So, good morning, students. In the last class, we are solving this problem, and we are somewhere here. We did not solve it completely. We have to solve it now. Like you have to find out the temperatures that is left out. For finding out the temperatures, you can take out this resistance circuit. This resistance circuit you can make use of, and using this resistance circuit, you can write the formula for Q. The Q formula will be like Q is equal to, here, T1, T2 has to be found out. So I'll make use of this one. T1 minus T2 by R steel I will get. The temperature difference by corresponding resistance I have to take. Now, if I do this, I will know what is T2. Then I can use T2 minus T3 by R insulation. This is R insulation 1. Now, if I do this, I will know T3. Then I'll make use of this. Then T3 minus T4 by R contact. This is R contact. This is R insulation 2. So that is equal to. If you do this, you will know what is T4. You can write it as T4 minus T5 by R insulation 2. So these are the formulas for finding the various T values now. So find out the T2 value using this. So T2 will be equal to Q into R
So
steel.
is it minus 196?
What minus 196? T1
T2.
value are speaking.
T2, sir.
T, T1 itself is minus 196.
This is
T2
point
will
one one nine.
also what?
1 minus 196.119.
You are telling the value, na?
T2.
T2 value you are telling, huh?
Yes, sir.
I don't have it with me right now.
Sir, it's actually
Mean value.
minus 195.88.
Yeah, yeah. Let me check it. Wait. This is our steel. So plus T1 you will get. So you substitute the values. The Q value is, this value should be like minus 195.88 degrees centigrade. The Q value is already known to you. It is 76.6. The R steel value is known to you from this expression. So R steel is known to you, and T1 is known to you. Substitute the values. You will get the T2 value. So that's the thing. And we'll move on to the next one. That is T3. For finding out T3, it is Q into R insulation 1 plus T2. Substitute this minus 195 here, you'll get this. Then
Minus 8.73.
minus 8.73, yeah?
Yes, sir. I mean,
Degrees centigrade. Good. So Q. If you want T4, make use of this expression here. Make use of this expression. So if you make use of it, it will be like Q is equal Q and T4 is equal to Q into R contact plus
minus 8.62.
check. Sorry, my device got disconnected. Somebody is telling me the value. Rahul, please tell me.
Minus 8.62 and 27 point something 93 or 33. 27.3.
Degrees centigrade. So these are the temperature values. that you can find out. Okay. Along with this, he's asking you one more thing in this question. Okay. He's asking overall heat transfer coefficient. Okay. He's asking you to find what is overall heat transfer coefficient. Okay. First, let me explain what is overall heat transfer coefficient concept to you. Overall heat transfer coefficient. This overall heat transfer coefficient you can apply anywhere, not only in this particular sphere. Okay, it can be for slab or cylinder or sphere. Anything it is applicable. So let me explain this using the slab concept itself. Okay, I have a slab here, and then there is a atmosphere T infinity 2 here, T infinity 1 here, T1 here, T2 here. So using slab I'm doing. So if I take the resistance circuit here, this is the resistance. These are the three resistance circuits that I'm going to get. This is T infinity 1, this is T1, this is T2, this is T infinity 2. And this is R convection 1, this is R conduction, and this is R convection 2. Okay. Now, if I have to write the Q formula here, the Q formula goes like this. The Q is equal to delta T, that is T infinity 1 minus T infinity 2 by the resistance I want to take here. The resistance is like R convection 1, if I take it is 1 by H1A plus R conduction, if I take it is L1 by K into A plus if R convection 2, if I have to take 1 by H2A, I will get. So I want to transform this equation into this form, which form Q is equal to A into delta T. I want to transform this. Okay, I'll get some constant here. Okay, I'll get some expression here otherwise. So if I transform this expression into this form, what I get is Q is equal to the area that is there in the denominator. I'm going to take it in the numerator, and I'll be left out with 1 by H1 plus L by K plus 1 by H2 into A into delta T. So what I'm trying to do is Q is equal to some expression. Let me call that expression as U into A into delta T. I want to write it like so. If I write the expression in Q is equal to U A delta T form, now this U will turn out to be 1 by H1 plus L by K plus 1 by H2. So this particular U is nothing but your overall heat transfer coefficient. Overall heat transfer coefficient. And what will be the unit of this overall heat transfer coefficient? Can somebody tell me? What is the unit of this overall heat transfer coefficient? It is nothing but watt per meter square Kelvin. Because it is 1 by 1 by 1 by H. Simply it is 1 by H. Because it is simply H. So if you have to take the unit of H, it is watt per meter square Kelvin. So you will have the unit of watt per meter square Kelvin. So U is nothing but the overall heat transfer coefficient. Find out this way. Now, if you want to find out this particular U in this particular problem that is given to you here, so for that, what you have to do, you have to take this one. Okay, Q is equal to R total and all these things is there, no? So in this R total, that A has to be taken out appropriately. Okay, when the area is taken out appropriately out of this, you will get what is U. Okay, that is the way to find out your U. Okay, right. So there are two ways of finding U. U is equal to 1 by the resistance total, and this resistance total should not have area in it. Whatever the area that is there in it should be neglected. So for that, you have to multiply the area here, area into R total. That is one way of doing it. The other way of doing U is simply Q by A into delta T. This is one way. So anyway, you can do it. Q by A delta T you can take. So in our case, you got Q value here. It is 76. Is it 76 or 76 point something? 76.6 by the area 4 pi R2 square. When I say R2, this is R2, the outermost one. The radius is R4 here. Okay, 0.29 meters. So you put it as R4 itself. R4 square into the delta T. The delta T value is minus what are the values for the delta T here? Minus 196, and the other one is what is given in this question?
Minus 30. 30.
Minus 30, yeah? Minus 30 or 30? It is given as 30 in the
30.
question. Okay, 30. Using that, you can substitute the values here. Minus 196 minus 30. You substitute. Anyways, a minus you will have here. This minus will go off. And this R4 is nothing but your 0.29 meter. Substitute the values, you will get what is the U value in watt per meter square Kelvin. Okay, so this is one way of doing it. But look at your problem. In your problem, what he is saying is this U he wants you to find based on the outside surface area of the metallic vessel. Okay, outside surface area of the metallic vessel only you have taken, but the delta T you have corresponded for the whole thing, the calculation that you have done. So if you want it for only the outer shell, only outer means Q by A into delta T will be like minus 76.6 by 4 pi into 0.29 whole square into the value will be like minus 30, and the other value that corresponding to this is 27.93. The outer surface is having this much. That 30 is the temperature of the atmosphere, so it should not be minus plus 27.93. Yeah, how much it is? 93. Yeah. So you will get U value. Yeah, this you take it as positive, so that U value will be positive. So is it clear till now the overall heat transfer coefficient concept and the calculation here? Any doubts you are having? Is it clear? Tell me this U value. What is the U value?
Total is 0.30827.
Total is 0.30827.
827.
Okay, this one.
Minus 35.01.
35.01, you take minus instead of minus, you put plus here, or you take this minus and this plus. Okay. Anyways, you have to get the plus here. So for that, you have to make the appropriate changes. Right. I hope it's clear to you, and let's move on to the next concept. And the next concept is here, radiation heat transfer coefficient. Overall heat transfer coefficient just now we have seen. And the next thing I'm telling you is radiation heat transfer coefficient. And this radiation heat transfer coefficient is also same thing. It can be for slab or for cylinder or for sphere. Okay, for anything you can apply. Okay, although I'm telling it under the sphere section, anywhere you can apply this concept. So that's the thing. So Q by radiation, we know it. What is the formula? It is a Stephen Boltzmann constant, which is equal to sigma into epsilon into A into T to the power of 4. Let me call it 1. T to the power of 4. T2. Okay. So this is your radiation heat transfer. But similar to your overall heat transfer coefficient, this one also I want to express it like Q is equal to something into A into delta T. This format I want to transform this. I want to transform this equation into this form. So for that, what I'll do is this Q radiation, I will write it as sigma into epsilon into A into this T to the power of 4. I can write it like T square minus I can write it like this. Okay, this is square and sigma into epsilon into A into, if I write this as same, and if I further extend this, it is T1 plus T2 into T1 minus T2. Okay. So what I have here is sigma into epsilon into T1 square plus T2 square into T1 plus T2 into A into T1 minus T2 I have. So now if you look at this equation, this Q radiation is equal to sigma into this whole term, you keep it aside, and A into delta T. So what I can do is here, Q radiation is equal to this term, I'm writing it as H radiation into A into T1 minus T2. So that using this, you can define what is your H radiation. That is heat transfer coefficient by radiation. Okay, or radiation heat transfer coefficient. Anyways, you can call it. If you want to quantify this, this is equal to sigma into epsilon into T1 square plus T2 square into T1 plus T2. So this is how you will get your H radiation. And what will be the unit for this H radiation? H radiation will be measured in watt per meter square Kelvin. So that will be your H radiation. Story. Okay, I hope this radiation heat transfer coefficient is clear to you. Any doubts you can ask, or I'll move forward. Yeah. So, so far what we have done is we have looked into the cylinder concept, the slab concept, the sphere concept we have seen. And if you want to, summarize what we have seen, okay, for the summary purpose, I'm telling you this. So now all of you keep your book horizontal and try to draw the table that I am drawing here. Okay, so there is a table here, and in this table, let me take. See, what I'm trying to give you here is a summary of what we have already seen. So in this, what we will have in the first is governing equation. So the first thing is your governing equation, and you write it for all the remaining three things. Okay. Likewise, you do for all the things like whatever that is repeating. What else you have in the next place after governing equation? You will have something called as general solution. Once you get general solution, you will also get what is called as temperature variation trend. Temperature variation trend you will have. And what else you will have? Temperature variation equation you will have. Temperature variation equation you will have. And then R, you'll get Q formula first. Once you get Q formula, you will also get the R formula and so on. Okay. Like this, so many things can be written. You can also include a figure here. Okay, in this thing, you can include a figure representing the appropriate nomenclature in the figure. You can draw it. See, this gives you the summary of whole thing that we have done. Okay, I'll cover one more concept. Okay, parallel resistance. Parallel resistance in cylinder and sphere. Parallel resistance in cylinder and sphere. Okay. Can you tell me one example wherein you will have a parallel resistance? See, so far we have been seeing the series resistances like this. Okay. Can we have a parallel resistance like this for cylinder or sphere? Did we solve any problem of this kind in cylinder and sphere? Did we come across this parallel concept in cylinder and sphere?
No.
So far you did not get it. Okay. So So there can be a chance of getting this parallel concept even in case of your cylinder and sphere. And when can that happen? Okay, it can happen when you are having a sphere or cylinder. Let me draw it properly. This is a sphere. And then it will be having so and so temperature here. Here you will have T1, here you will have T2. Okay. See, whatever the T infinity 2, this is T infinity 1 we generally take. Whatever the heat transfer that happens between this T infinity 1, sorry, T2 and T infinity 2, this can happen either by convection or by the radiation. So far, what you have done is you have considered it with respect to convection only. Okay, it can happen by radiation also. If that is the case, okay, so what will be your resistance circuit? You have to draw it here. Initially, you will have the resistance due to convection inside. And then resistance due to the conduction through the cylinder or the slab, sorry, cylinder or the sphere. And then the third one, okay, let me write this first. R convection inside. This is R conduction through the cylinder or sphere. Both the ways it remains the same. But if on the other side, if you have convection happening and you have radiation happening, you cannot have only one resistance circuit here. You will have two resistances. Okay, and those resistances will be in parallel. Okay. So this will turn out to be this way. Here you have T infinity 1, here you have T1, here you have T2, and here you have T infinity 2. So this will correspond to the resistance of convection, and this will correspond to the resistance of radiation. Okay. If this is the case, your resistance formula will be resistance due to convection is equal to 1 by HA. Anyways, you will write it. But resistance to radiation, if you have to write 1 by H radiation into A, you will get, where H radiation is equal to sigma into epsilon into T1 square plus T2 square into T1 plus T2. That's how the H radiation is defined. And if you have to take the overall resistance, R total here, this will be R convection 1 plus R conduction plus R equivalence you will take. where R equivalence will be measured by 1 by R equivalence is equal to 1 by R convection 2 plus 1 by R radiation. Okay, this is how you'll get the R total. Okay, this is R convection 2, this is R radiation. Yeah, is it clear? I hope it's clear. If you have any doubts, you can ask. In the afternoon, in the lab session, I'll take the lecture. In that lecture, I'll cover a problem based on this concept. It will be even more clear to you.